This conference will now be recorded.
So this is the second day of our mini series provided by our colleagues at NOPP, for which we are very grateful. Very interesting two talks last time, and today we continue. So this is a Hurricane Coastal Impacts Forum, right? And we have this seminar and two more in July. So next week we won't have anything, but the week after and 3 weeks from now we'll have two seminars. After that, guys, my seminar schedule is wide open. So, and NOPP cannot provide any more speakers, unfortunately. So give me a call if you want to present and help me fill up the series for the rest of the summer and fall, right? With all of that, I give control to Alan and his colleagues at NOPP. And guys, thanks again for this great opportunity. And we're here to learn. And now you run the show, please.
Got it. Great. Thanks, Alex, for that framing and the context, and also, of course, allowing us to piggyback on your seminar series over these weeks. I want to thank everybody for joining us today for a few presentations about the National Oceanographic Partnership Program, or NOPP as we commonly refer to it, Hurricane Coastal Impacts Project. My name is Alan Leonardi. I'm the director of the NOPP Program Office, and I will be your MC and moderator today. The NHCI project that will be discussed as a part of this series are all efforts that are supported by the National Oceanographic Partnership Program with primary funding from the Office of Naval Research and the National Oceanic and Atmospheric Administration, and participation across all sectors. Today's discussion is the second in a 5-part series and will include 2 presentations. The first presentation by Dean Gesh of the USGS will focus on the role of accurate land surface representation and coastal elevation models and that it has on forecasting hurricane impacts. The second presentation will be by Jenna Brown, also of the USGS, and will focus on efforts to study the evolution of storm surge and waves and their importance for hurricane coastal impacts modeling, especially across natural and man-made landscapes. Each presentation is intended to last approximately 30 minutes, including a 10-minute question and answer period. For ease of discussion using this virtual format, I ask that you refrain from asking questions until the end of each presentation, where I will attempt to moderate the Q&A, both virtually and, of course, over the chat system. I will now hand the virtual microphone over to our first speaker to get the conversation started. Dean, the floor is yours.
Thank you, Alan. Share my screen. Okay, thumbs up. Good, must be coming through. Yeah, thank you for the introduction. I'm today's first speaker. Bear with me just a second. Okay, we'll get right into it here. So yeah, the NOPP Hurricane Coastal Impacts Project, or what we just call NOPP here, NOPP Task 1, digital elevation models, but it includes much more than that. As Reggie Beach introduced last week, forecasting hurricane impacts, where they occur and what type, for instance, flooding, erosion, structure damage. The greatest uncertainties are on the land. So this task addresses those land factors that affect forecasting impacts. And a strong emphasis on remote sensing and all the parts of this task. The 4 objectives that you see listed there: digital elevation models, vegetation characteristics, sediment type and grade, and then structures and infrastructure. So big emphasis on remote sensing. It's the primary source in all 4 of these, and then also a big component with AI, ML, especially for the last 2. So I represent a team of 8 principals and others, some other students. I want to acknowledge that up front. The work presented here today is accomplished by that team that comes from both government, academia, and industry. So overall, the NHCI study area is the Gulf and Atlantic coasts. I think this was touched upon last week. Obviously, the hurricane impact areas. And then for this task, we also have what we call focal sites, and those are listed there. the Outer Banks, North Carolina, and then an area in the Western Deltaic Plain of Louisiana. And I have some examples about why we have some of these focal sites there, but those were selected for specific reasons. We'll have more of that in a bit. Topobathymetric elevation models, or what we call TBDEMs. I'll introduce that term if you're not familiar with it. So that's basically a merged rendering, seamless representation of the land-water interface. So we have the topographic data and the bathymetric data, and those are a merged rendering. So it's very important for this type of coastal modeling. Some of the elevation data sources that are listed there. And a real important component of this is rigorous handling of the disparate vertical datums of the topo and bathy data sets. So those were collected for different reasons and with different systems. So the topo data on the land side is often referenced to an orthometric or a mean sea level referenced datum. And on the bathy side, on the water depth side, the bathymetric data is often referenced to a tidally referenced surface of mean high water, for instance. So we do a rigorous adjustment of those to make these a truly seamless data set. A very important tool that's produced by NOAA called VDatum. It's a tool that we use for these critical datum transformations. We have two main sources of these TBDEMs, and I'll touch upon both of them. The first is a USGS product known as CONED, Coastal National Elevation Database. Some of the specifics there that you can see. Along the bottom there, note that there's numerous modeling systems that use these CONED products, including the National Water Model. Some of these other coastal modeling systems are in use by our modeling teams on the NOPP project, NHCI project, and you'll hear much more about that when they present in future weeks. So basically, the modeling teams take these topographic bathymetric digital elevation models, or TBDEMs, reformat those to what they need specifically for their specific model. So density, resolution, and format are transformed from the basic format that they're produced in. The second main source of TBDEMs is what's known as CUDEM. That stands for Continuously Updated DEMs, and these are produced by NOAA, NCEI, or the National Centers for Environmental Information. So I'll have some more details on both of these. So CONED, Coastal National Elevation Database, and CUDEM, or Continuously Updated DEMs. These are coastal elevation sources. So a brief overview of the production procedure or the workflow. This is specific for CONED. It's a very similar workflow for production of the CUDEM. But the important steps there, again, the disparate data sources, topography and bathymetry, and then a lot of spatial processing that's done for integration, again, including this real critical component of adjusting the vertical datums. So getting all the coordinate systems and the units and the referencing, both horizontal and vertical, into the same spatial framework, that takes place as part of this workflow there. There's a reference there on the bottom for a paper that has a lot more detailed information on the CONED. So refer to that for more information if you're interested. Just an example of CONED model for the Northern Gulf. This is 1 meter data, 1 meter spatial resolution data. Comes from many different sources, as it's shown there, different topographic data sources, and then many bathymetric sources. So you can imagine how all the processing that has to go into that to merge those into a common spatial framework. One of the important parts is what we call spatially referenced metadata, or just to refer to it short as spatial metadata. And that's kind of that black box there on the upper left that lists the different sources. So this retains all the source data characteristics on a polygon footprint basis, so that for any location in the elevation model, you can always refer back to the source data that was used to construct that model. Just another example, and then the technical specifications. Not going to go through these in detail, but I will mention again that the nominal resolution is 1 meter data. Now, obviously, some of the bathymetry data doesn't have that original spatial resolution of 1 meter, but it is regridded to match the topographic 1 meter data to make this seamless representation. Just some graphics of some other example areas. This was the Hurricane Florence impact area in the Carolinas and along the Georgia coast. Some of them are more recent data that was produced there. Again, LiDAR data is a big source, topographic LiDAR data and also bathymetric LiDAR data. Those are the best sources right along the shoreline, the coastal land-water interface. So that's the preferred source, but then there are other sources that are used in construction of these models as well. Some more examples. This is current work that's going on in Florida. You can see some of the details in the Florida Keys there. Again, high resolution, high accuracy LiDAR data that's merged together with all the bathymetric sources to make these elevation models. Another graphic of this current Florida development. This includes lots of new topobathy LiDAR right along the shoreline, so very up-to-date data that's being incorporated. And then there's also being a lot of new offshore bathy surveys that are being collected that are being incorporated into this Florida model. So we produce these in regional areas and then piece them together for kind of the national. Okay, some more details about CUDEM, or the continuously updated DEM. This is the NOAA product. Again, general workflow, it's very similar to the NED, and the important part again is this conversion to common vertical and horizontal references, specifically or importantly the vertical datums that go along with that. So it's a diagram that shows that. And then some examples of recent CUDEM products in some of the areas, specifically in the NOPP project areas. Last year, all new data in the Maine to New Hampshire to Massachusetts region in the Northeast. Some examples there. Good flavor of that type of data. And some more new updated data in the CUDEM for New York and New Jersey. Again, graphical representation of the elevation, the quantitative data that goes behind that. A list of the technical specifications again of CUDEM, very similar to CONAD, but with some differences. One of the main differences is it's a geographic projection, whereas the CONAD is in a projected UTM projection. The spatial resolution is a bit different for the CUDEM products. 1/9 arc second in the geographic coordinate system, that's about a 3 meter resolution versus the 1 meter resolution for CONAD. So some slight differences there, but a lot of the same input data and production methods. And also a really good recent paper that has a lot of much more detailed information on CUDEM. So I'll refer that to you if you're interested in that on the lower right there on this slide. The CUDEM also has spatial metadata, as an example of it here. So just like the CONAD, so very important that a user can trace back to the source data that goes into it. And then where this is also important is the variable accuracy, because as you can imagine with all these different sources, both on the topographic side and on the bathymetric side, there's big differences in the accuracy and quality of the data. So that information is available to users and can be displayed and queried in a GIS environment. A map of the coverage of CUDEM. So we've got full coverage of the NOPP project area. One thing to note here, the 1/3 arc second, that's about a 10 meter resolution. That is in the more offshore, just in the bathymetric areas. The actual TBDEM along the shoreline and the coastline is the 1/9 arc second, or the 3 meter resolution. So these two products, even though there's some differences, they're highly complementary. In fact, CONAD even uses some of the gridded bathymetry from CUDEM for some areas. So there's we work cooperatively to produce these models and apply these, but there is some overlap. So one thing we've done for the NOPP modeling teams is an index of where the best available data is from CONAD and where it is available from CUDEM. So there's a guidance for the best available data that can be used for any particular area in the NOPP project area. So this is where the source data are the best, the source date is the most recent, and the accuracy is the best. And that comes from a combination of both CUDEM and CONED. One thing that is also done with these products is there's updates, both after hurricanes. This is an example where pre-Hurricane Michael data was produced. The standard product from CUDEM was constructed from post-hurricane data. So for some of the hindcasting that was done by the modeling teams for Hurricane Michael on the NOPP project, beginning of the effort, we needed the pre-hurricane, so we went back to some of the older data and produced that, and then you can see some of the changes there. There's a breach that was through that barrier island near Cape San Blas as a result of Hurricane Michael, so an example of that. And then some of the new, again, some of the newer data has where there's new LiDAR data that's been flown after hurricane, in this case, after Hurricane Irma, that's been incorporated into these models as well. So the idea is to keep them up to date as much as possible for use in the modeling. One of the issues or challenges is as you move inland from the coastal areas, so the rivers that flow into the coastal areas, there's depth data for some of that. So as a storm surge propagates up these stream channels, bathymetry is very important. Unfortunately, we don't have that in all places, but where it does exist, it has been incorporated. So that's some of our current research is looking at how to improve these models with those information. At least what's useful to the modelers is where there isn't data, there's a mask that's provided of where there's no bathymetry data, because that can have an effect then on the propagation of the storm surge model onto the land surface. Okay, on to the next main component, the vegetation component. Our team also works on that. So it's a critical land surface variable for these morphodynamic change models. And the key component here is what's known as Manning's N. That's a factor of the roughness of the bed friction for propagation of the water flow across the land surface. And that's directly related to vegetation. A couple of papers where this is well known and well documented. So the idea here is to produce high resolution, up-to-date vegetation maps that can be fed into the models, and that's what's done as part of this task. So we take advantage of the high resolution of recent imagery. This is NAPE imagery, the National Agricultural Imagery Program, Agricultural Inventory Program. So that's a nominal 1 meter resolution, much more recent. So we use a machine learning approach, in this case random forest, to produce a very simplistic map of land cover categories at the land-water interface, and then that's fused with a much more detailed thematic information from the NOAA CCAP product to bring in the higher, more information, more detailed information about these land cover classes, and then can associate this Manning's N factor with that. And that's been done for the entire NOPP area, just a map there that kind of shows the status of those. Variable dates on the NAPE imagery, so it's as most up to date as possible. And then that's available for the models, and it's been used by the modelers for their results. Another component that's important for some of the models is the vegetation height that's used. And so contemporary vegetation height is used in some of the models. We're also deriving that from recent LiDAR data, what's known as height above ground, where the difference between the height of the vegetation as sensed by the full LiDAR point cloud and then the height of the ground. The difference between that is the height of the vegetation, or that's known as height above ground, so derived from the LiDAR data. So that's also being produced for these same coastal areas, and complements the vegetation class that came from the previous product. So just some examples there. There's not quite full coverage of the NOPP area, but for most of it, that's being produced and is also available. Another thing that's important is the kind of brings together the elevation component and the vegetation component is the air that in the elevation models. That's very important to consider the vertical error in these elevation models. So these LiDAR produced elevation models, the vegetation, although it's removed, can still have an effect on the accuracy of the elevation models. So we've done some work looking at characterizing the quality of the elevation data dependent on the type of land cover that was available or that exists in those areas. And a recent paper just published that documents a lot of that work. Leads us into this whole idea of TBDM uncertainty. So that's an active area now. We know that there's variable vertical accuracy associated with these elevation models, and so bringing in the vegetation component and then also the source of the data and supplying that as ancillary information that goes along with these models so it can be propagated into the results. Another part of our team's work on vegetation mapping, in this case, also the coastal vegetation mapping refers to updating the information. So if there's been a change after a storm, or if the data itself are older, this is a tool that's been developed to produce this high resolution elevation data, vegetation data for these coastal areas. And I'll step through this real quick. So again, the project need goes right back to the importance of this Manning's N factor for roughness and friction for the flow models, and how the different vegetation classes have this different roughness factor that's associated with it. So how do you update these models? Because the vegetation data itself doesn't get updated all that frequently, kind of nominally on a 5-year cycle. So we know there's changes. In some areas we need a different method to do that. So this is a tool that's been developed, uses a Jupyter notebook application that operates on planet imagery. And then it can produce updated elevation maps for these unlimited number of classes, and it's a highly automated process. So these Planet products, this is a commercial satellite system, Super Dove satellites. It's 8-band imagery, multispectral imagery that's used in a machine learning application, random forest, to produce these vegetation maps. Right now, it's working in our areas of interest. These are our focal areas there in the North Carolina, Mississippi, and then part of the Florida coast. So it uses this approach, highly automated approach, and produces these highly accurate maps based on recent imagery, this planet imagery, to update the vegetation mapping. Again, it's highly automated. That's what comes from the Jupyter notebook, and it kind of guides a user through selection of images, and then runs the classification, and then produces these updated maps. Just some examples there, again, with a good high accuracy. One model, machine learning model, works for all these areas, so some nice implementation there. And then there's a complete user manual that goes with that to help guide the user. There's a user interface, but then it also allows, because it is a Jupyter notebook application, it allows customization and modification for the users that want that capability and have that knowledge to do that. Last two things I'll go through quickly here is another part of it is the land surface variables is sediments. So this work's led by Dan Buscombe, part of our team. And this is the coastal sediments component of this. So the idea here is to be able to predict the sand grain size on the beach face or in the intertidal area. And that's being done with a very data-centric approach. There's kind of little hope of modeling the grain size dynamics over these large areas. So it needs to be a data-driven approach. So it's based on a large sample database, and then uses a machine learning approach that pairs that with relevant hydrodynamic and morphologic variables to predict the grain size and the sediment characteristics. It's the database itself. Seagrasp is this database of some 5,500 locations. many in the U.S., but some outside that are used to train the machine learning model. Again, it's data driven, and with these different variables. So looking at wave statistics, tide range statistics, and beach morphological variables that are derived from remote sensing, basically the slope of the beach that can be gotten from LiDAR, and then also shoreline change from a history through satellite imagery. So all those things are fed into the model, and then to produce an estimate of the sediment characteristics. Just some summary there, very brief overview of this, but kind of one of the most important things is the morphological variables such as the beach width and the slope and the shoreline variability. Those seem to be, at least in initial results, more important than the wave variables for predicting the grain size and sediment characteristics. And then last, just a couple things on some of the initial research and tool development that was done for improving structure data. Obviously, structures are important, affecting the flow, but then also the damage characteristics. So part of the team has also done some work developing some of these initial tools for improving structure mapping and damage assessment, modeling the coastal hurricane impacts. And then lastly, just want to acknowledge the team members. So a number of us from USGS, different science centers, USGS, and then from NOAA and different universities, and then a whole host of students that have done some real good work to support a lot of this. So I will end it there.
Great. Thanks, Dean. I appreciate the presentation. We have time for maybe one or two questions before jumping into the second presentation. And I see that Jamie Pringle has a question in the chat already, which is there a product that takes the QDIM and extends it to the deep ocean, for example, off the shelf break, with a consistent vertical datum, perhaps for things like ocean modeling?
Yes, NOAA does have other products. I think it's called Coastal Relief Model, which does extend it further out. It's a bit less resolution. I think it's 3 arcsecond. I'm not sure about the consistent vertical datum, because I know some of that is based on older data where maybe the vertical datum wasn't even exactly known. But there are kind of a nesting of models, if you will, that NOAA produces that do go further out. Coastal Relief Model is the name of one of them. So, yeah.
Great. Any other questions from anybody in the audience before we jump into the next presentation? You certainly can ask them at the end as well.
Yes.
Okay, seeing and hearing none. Jenna, I'd ask you to take the floor and go ahead and present our second presentation of the day. Appreciate your presentation, Dean, and Jenna, whenever you're ready, the floor is yours.
Okay. Getting my presentation started. Okay. Thank you. Yeah, my name is Jenna Brown. I'm a researcher with the USGS. Also going to be presenting with my colleague Isabel Houghton from So Far Ocean. And this represents work being done by a large team of people. And so our task within the NOPP Hurricane Coastal Impacts project is to collect in situ both real-time and recorded measurements of hurricane-induced hydrodynamics and flooding. So this includes waves and water levels in the near shore. And so to put our work in context with the rest of the project, here I'm just showing an example from Hurricane Ian and the different domains of each task. And so we're one of the tasks collecting in situ hydrodynamic measurements. And so there's going to be teams that you'll hear from in future seminars that are air deploying drifters offshore to measure waves in deep water within the path of the hurricane. And then as the storm approaches the coast, we're tasked with documenting the height, extent, timing of storm surge and waves as they evolve in the near shore and then dissipate across natural and man-made landscapes. And so these observations are critical for providing ground truth conditions and for helping to validate and improve our hurricane coastal impact models. And so our work is building upon the vast experience of the USGS in land-based rapid storm sensor deployments. We have a USGS storm tide monitoring program, which was developed to collect storm tide and wave data at locations within coastal areas threatened by storms and flooding impacts. And so on the left, you can see the spatially dense and expansive network of sites that we've created, where each dot represents a location where there's either a permanent gauge installed or where a sensor has been temporarily deployed in the past, and also locations where we've pre-identified and pre-installed brackets like the one you see on the right, and pre-surveyed those in to facilitate quick sensor deployments ahead of storms. So we have really good spatial coverage along the coast with that network, and then the data that are collected from our storm response is provided on the USGS flood event viewer, which is shown in the middle here. And so you can see all the different types of sensors, data that we provide, including high watermark that are conducted after a storm. And so this is an example from Hurricane Ian, where we had a number of offices and teams deploying those sensors ahead of the storm. And so the storm responses are coordinated virtually by the USGS Coastal Storm Team, which is activated as necessary when there's a storm approaching the coast. It's a large multidisciplinary group. You can see all the federal partners that join the calls, as well as state emergency managers and academic partners. And the goal of these calls is to coordinate and communicate the USGS response from a regional to a local scale, and using just well-established protocols and communication channels to facilitate smooth and safe deployments. And so our NOPP deployments are planned in coordination with the USGS Coastal Storm Team. But we're looking to expand upon those spatially dense sensor deployments by the USGS along the coast and provide detailed measurements of water levels and waves in shore perpendicular transects, so spanning the nearshore region across the surf zone, beach and dune, and covering the inland flooding extent. And so deploying sensors in these transects will allow us to measure the arrival, transformation, and dissipation of waves and water levels. And so we're particularly focused on collecting more observations seaward of the dune and extending out to the 20-meter depth contour. And so this will allow us to relate the offshore forcing conditions in deep water to the extremely dynamic surf zone and shoreline conditions, and then the subsequent impacts on coastal barriers and communities. And in particular, we're looking to use instruments that have high sampling frequency so we can really capture the range and full spectrum of storm waves. And then we also, when possible, want to deliver these measurements in real time. And so our approach to meet these objectives is to utilize existing piers and other infrastructure for shore-based deployments and deploying those instruments in cross-shore transects. And we're using a combination of in situ and non-contact sensors. And so here I'm just showing kind of an idealized transect where onshore we will have a weather station that is transmitting that MET data in real time, and then across the inland and across the dune and beach, we're deploying some self-contained, battery-powered internal logging pressure sensors with up at least an 8 hertz sampling frequency or greater. And you can see we put those on brackets and attach them to things like light poles or walkways and railings on the back beach. And then as we move down the beach and to the shore, we're attaching those to the pier pilings and trying to extend those measurements as far out into the surf zone as possible. And so after a storm, we go and retrieve these sensors, and then we can post-process that data, correct for atmospheric pressure, and calculate our mean waves and water levels. And then moving out into the surf zone, we're deploying, we're utilizing the pier railings and deck and deploying non-contact radars. And so these are actually looking down, directly measuring the sea surface elevation, and then computing mean water levels and waves on board. And so we've also paired this with a cellular modem so that we can transmit those mean waves and water levels in real time. And we're also capable of transmitting the 5 hertz raw elevation data. And so that also can be used to post-process in different frequency ranges after the storm. But most important, that allows us to preserve our data in the event that we would lose the sensor or something during the storm. We have the most valuable part, which is that data. And so the USGS is leading these shore-based deployments, and then we're working with our partners at SOFAR Ocean to deploy a sensor in about 20-meter water depth offshore of our pier sites. And so this will allow us to relate the offshore forcings to the nearshore and coastal impacts. And so throughout the project, we've iterated through various strategies to achieve the deployment at this location, and we're going to talk about that a little bit more later in the presentation. And so just quickly touching on the obvious challenges for our group, we're working in this extreme environment where it's already notoriously difficult to deploy instruments in the nearshore region, let alone have them withstand hurricanes forces and stay in place during a storm. And then we're trying to deploy those rapidly. So typically we have less than 5 days to make a plan, mobilize, deploy, and get our team back, retreat out safely. And so just not a lot of time to deploy these instruments. And then we're also dealing with the uncertainty in where to deploy. So using all the models and predictions, we're tracking the projected landfall, but we know that continues to change and move as the storm approaches the coast, and we have to make a decision ahead of time. So selecting those correct locations for deploying our transects is difficult, and then the logistics of just getting the equipment and personnel in place to be able to respond to a storm anywhere along the U.S. Atlantic and Gulf Coast, and getting the sensors at 20-meter water depth are really big challenges. But we've found ways to address and overcome these challenges, and so that leads me to our some of our notable achievements in the project so far. So the first is the development of this non-contact self-contained radar for measuring waves and water levels. And so we're using an off-the-shelf Geolux oceanographic radar sensor paired with an internal data logger and also a cellular modem for data transmission. And this can be deployed temporarily on a pier railing, so it's non-intrusive, and it really allows us to extend those measurements into the surf zone. And like I said, we configured it to transmit the raw 5 hertz high frequency sea surface elevation data so that we can preserve that data and post-process it at a later time. And so we've been testing and operating radar at the U.S. Army Corps Field Research Facility for, I think, over 2 years now. And so on the left, here's the box housing our radar and data logger, and then you can see the plan form of the field research facility, and our radar is at the end of the pier, and we can compare with water level measurements by the NOAA tide gauge, as well as water level wave measurements by a bottom-mounted, upward-looking acoustic Doppler current profiler in the Army Corps transect. And so on the right, just showing a comparison of those results. On the y-axis is the radar measurements, on the x-axis the other instruments. We have nearly 1-to-1 agreement in water levels. Just noting there's just an offset in the Army Corps depth because it's bottom mounted and not accounting for that height above bed, but still good agreement, and as well as good agreement with the waves. So we feel pretty confident about deploying these radars and collecting accurate data during storm events and extending our measurements into the surf zone. And so then another challenge is how do we collect that data at the 20-meter depth? And so working with SOFAR, we originally had planned to deploy a SOFAR spotter buoy and smart mooring, which you can see here, where the buoy's at the surface measuring the waves, moored to a pressure sensor at the bottom measuring water levels. And we really found it wasn't feasible to deploy this this system in particular by air or even vessel in a rapid response sense. So for the 2022 and 2023 storm seasons, we opted to pre-deploy those at select pier sites, and those are shown here. And so we still had pretty good coverage during the storm seasons, and fortunately had a buoy in the location where two hurricanes made landfall during those storm seasons. And so probably our greatest accomplishment so far has been the successful rapid deployment of sensors ahead of 3 major storms. In 2022, we responded to Hurricane Ian. We just had 2 field technicians deploy a transect at Clearwater Beach 2 days before landfall, and then move to Panama City Beach 1 day before landfall and install a total of 15 sensors. And then we reoccupied that transect at Clearwater Beach in 2023 for Hurricane Idalia, deploying a total of 6 sensors. And then also in 2023, we responded to Hurricane Lee in the Northeast along the Maine, New Hampshire, and Massachusetts coasts. And due to limited infrastructure, we deployed multiple teams and got sensors out at 10 sites, 4 of which did have a transect of 2 or 3 sensors each, for a total of 23 sensors. So next, I'm just going to highlight some more kind of comparisons and takeaways from these deployments. And so first, looking at Hurricane Ian in 2022 versus on the left, and Hurricane Idalia on the right in 2023. The top plots are showing the forecast about 2 days before landfall, and both seem to be indicating it was heading towards like the Big Bend area of Florida. And so for Ian, this is the information we had to decide where to deploy our transects. So we decided to put them at Clearwater Beach and Panama City so that we'd span either side of projected landfall. And then we see as the storm is about to make landfall, that storm shifted south, and so both of our transects ended up being on the left or the weaker side of the storm, whereas Hurricane Idalia, the track kind of stayed consistent and hit that Big Bend area, so our transect in Clearwater was on the right or the strong side of the storm. And so looking at a closer look at the transects we deployed and the data here, for Ian, we just had 1 radar at the end of the pier, and then pressure sensors inland and in this back marina. And because we're on that the offshore wind directed side of the storm, we actually measured a significant set down in the water levels, even out at the 20-meter depth and end of the pier. And our other pressure sensors were dry because of that offshore and negative storm surge. But we still measured elevated wave heights during the storm with over 3-meter waves offshore and over 1-meter waves at the end of the pier, which is pretty big for this area. And then comparing that to Idalia, we opted to put 2 radars on the pier to get more measurements across the surf zone, and then the pressure sensors across the beach. And here we can see that on the pier, both sensors measured elevated storm surge because we're on that strong side in the onshore directed winds of the storm, and then also elevated wave heights of almost 2 meters at the end of the pier and less mid-span. So we can measure really that crossword transformation of waves and water levels that we're looking for. And then in comparison to those transect surveys, we also had a Hurricane Lee deployment where this storm, it was not sure where it was going to hit. The coastline was a very long area to cover, and there wasn't a lot of infrastructure, so we opted to send out multiple teams of technicians. We shipped our sensors up to the offices in Maine and Massachusetts and had those teams deploy the sensors on structures like pier pilings, beach walkovers, and even drilling them into rocks and stuff. And that gave us the spatial coverage that we were looking for along the coast, with some sensors in transects as well. And so now just looking forward to our 2024 storm response plans. For our shore-based deployments, we're looking to deploy 2 detailed cross-shore transects of wave and water level sensors on either side of the projected hurricane landfall, and that's anywhere along the U.S. Atlantic, Gulf of Mexico coast, planning to get those deployed 2 to 3 days ahead of landfall. And so we've identified over 30 potential pier sites, which are shown in the green dots. And these are structurally sound in populated developed areas where we're looking to measure those coastal impacts and spatially distributed along our dense coastlines. And then we also, to meet the challenge of being able to rapidly get to any of these locations, we've staged equipment and personnel in different regions shown by the color boxes so that we can be as prepared as possible. And then for the offshore deployments, Isabel's going to speak next about a new instrumentation that we're utilizing to ideally deploy sensors along the 20-meter depth contour. And so these would be able to be connected to our pier sites, but also being spaced along shore gives us the coverage of and spatial variability in waves and water levels as the storms approaches the coast. And so I will let Isabel take it over now to talk about the new so far tech developments.
Sounds great. Thanks, Jenna. So as Jenna alluded to, the original plans really were to come in with these smart moorings. So these subsurface RBR pressure sensor and surface smart mooring. As you can imagine, rapid response in advance of a hurricane for that proved relatively challenging, and converting them into a form factor that made sense for aerial deployment just wasn't feasible. And so starting last year with some additional support from ONR, we pursued basically a new instrument that would allow us to get these wave and water level observations from the near shore. So what this animation is showing is actually some local testing of the form factor. So you can see completely different looking than, say, the traditional yellow spotter buoy, or say a moored buoy with the subsurface feature. So if you go to the next slide, that will show us kind of the motivation for this, which I think Jenna covered some, is that the offshore hydrodynamics and those boundary conditions really are critical to properly predicting the coastal impacts. So this figure from Vanderloot really well visualizes the difference between the computed and the observed. So computed in red, but the shaded regions are plus or minus 10% of these offshore hydrodynamic forcing. So whether that's wave angle, wave magnitude, or surge in corresponding colors. And you can really see the disparity between, or the discrepancy between the computed and the observed can oftentimes be accounted for by just 10% of a given forcing. And so the goal here is really to make sure that we have observations of these offshore conditions all the way in this perpendicular transect, such that we can ground truth these models and improve our actual coastal impacts. So how are we going to do this? Instead of a surface spotter with a subsurface pressure sensor, we are shifting to a fully subsurface bottom pressure sensor, allowing us to observe waves and water levels, but in a form factor that can be deployed from the air and doesn't have a surface signature, really limiting basically the survivability in these really extreme conditions at 20 meters. So if you go to the next slide, like I said, this rapid response deployable is kind of a key feature of this design, and also the capacity to have kind of high spatial coverage. Next slide. So here's a mock-up of the general rapid response design, where we have, with this project, as we'll talk about in following weeks, we have access to the Navy P3, their Scientific Development Squadron plane, and they have the capacity to deploy with open doors. So this isn't yet an A-size tube. Ideally, in the future, we'll be able to work toward that, but right now we need open door deployments. Through some testing iterations, we were able to arrive at a form factor that didn't need a parachute. So that means it really can pretty simply go out the door. It hits the water and sits at the bottom for 3 to 5 days. And then we have a galvanic timed release that just decays according to temperature and salinity, and releases that buoyant upper half of the instrument that, once it reaches the surface, connects to Iridium and dumps all of that data. So in this current form factor as well, it is a delayed time of telemetering the data. Ideally, down the road, we'd be able to build out to have a really minimal surface signature for telemetry. But right now, it's really about getting these ground truth observations for validation, retrospective validation. Next slide. So how did we build this instrument? So far has the full manufacturing production line for the spotter buoy. So that's that yellow buoy on the left. And effectively we took the brains out of that spotter buoy. So the electronics box that has all of the processing and firmware for collecting and sending data, and put that into an entirely new form factor using a bunch of bristlemouth connectivity, which is an open source standard that we've been developing for connecting any module that you want to the e-box. And so in this case, it's an RBR pressure sensor, allowing us to get really high resolution and high precision estimates of pressure at that 20 meter. That then goes into just a clean housing. So see on the next slide. And then on to the next slide. What this looks like in real life, not as clean as that mock-up. Some additional modifications from local testing included buoyancy. So getting the clean signal at the surface, really critical for making sure we're able to dump 5 days of data with high frequency data via Iridium on whatever battery is on board. As well as that minor cardboard collar just intended to stabilize the fall, because really robust instrument when falling vertically, when tumbling, definitely much more vulnerable to impact as we're deploying from an airplane at 150 miles an hour from 500 to 1,000 feet. Next slide. So how do we validate some of the observations from this instrument? This isn't a novel method for observing water levels or waves, very classic to put a bottom mounted pressure sensor, but definitely valuable to make sure that the data that we're getting in this form factor, in this deployment method, and the processing that we apply is reliable. So as mentioned, we have actually a performance record with these smart moorings where you have a co-located surface wave buoy, the spotter, and a subsurface RBR pressure sensor. So we dug through the archives of those data sets and looked for any conditions with high waves, and took a look at estimates derived from of wave height and wave spectra derived from the RBR pressure sensor and the longly validated spectral wave buoy, the spotter. And so on the next slide, you can see relatively good agreement across different conditions, where you had 4 or 5 meter waves at Ocean Beach here in San Francisco, and about 3.5 meter waves off of Puerto Rico. The slight discrepancies owing to a variety of explanations really in that near shore, these extreme conditions really capturing the timing of the peak and the overall magnitude pretty effectively. So that lends some good confidence there. And this is really, the secondary product, where the primary product is just the total water level. And RBR pressure sensors have extremely high Cool. The next slide showing wave spectra. So some processing that needs to be done to account for basically hitting a noise floor when you're observing pressure at 20 meters. You'll get attenuation at that depth of the wave signal. And that's why there's that vertical line of basically a cutoff frequency above which we wouldn't expect to get reliable observations. But you can see in the energetic frequencies matching the peaks and even secondary peaks relatively reliably, and also expecting to get the lower frequencies much more accurately than a surface wave buoy like spotter. So really exciting results there, giving us a good platform to work for this coming season. And so on the next slide, I think is my last one, just noting basically starting this project last spring in the past year, developed toward full end-to-end testing locally on the left, as well as some test flights with the Navy out of the P3. And so we're at our final form factor for building out 20 for 2024 operations, which is underway right now, and getting ready to deploy that picket fence to get that 20 meter observation in tandem with all of Jenna's and her group's work along the pier all the way to onshore to get that perpendicular transect. So I'll hand that back to Jenna.
Thanks, Isabel. And yeah, this is our last slide just to kind of go back and put our 2024 plans in context with the rest of the project. So you'll hear in the future from the Task 3A teams that are deploying in situ wave, looking to collect in situ wave measurements offshore in deep water. And then those can be related to the nearshore hydrodynamic conditions with this alongshore array of submersible spotters that Isabel just described. And this alongshore array will also allow us to measure the alongshore variability in waves and water levels and kind of narrow in on the storm path that Reggie mentioned. And then these measurements will be connected to our shore-based transect spanning the surf zone, beach dune, inland, describing timing and magnitude of the waves and surge and inland extent of flooding that will inform the coastal change and infrastructure damages that are observed during the storm. So that's all for us. Just acknowledging there's a huge amount of people that have worked on this with us, and we appreciate them. And that's all. Thank you.
Great, thank you, Jenna. And now we'll turn it over for a couple of questions if folks have them. There are a couple in the chat. There's also one comment, and I'll apologize in advance if I don't pronounce your name properly. Moji Rostaminia stated in the chat that you can also use Blue Topo high resolution bathymetry and provided a link to that at nowcoast.noaa.gov. So all good. And then George Rekirk asks the question, do you have any monitoring of water levels inland up our rivers and into estuaries?
Yes, USGS does maintain and operate some permanent gauges and stream gauges that are in the coastal area, and they'll also deploy rapidly sensors in the inland waterways ahead of these major hurricanes as well too. And so that data is either on USGS websites or on the USGS flood event viewer.
Great. Are there any other questions from anybody in the audience? I'm not seeing any or any hands raised, which is fine. Another great series of presentations. Oh, wait, we've got somebody speaking, I guess, if you
that's I don't know how to raise the hand, and I don't have time to type the question. I was just curious, those pressure sensors. I know in seismology, seismologists use pressure sensors, bottom pressure sensors that have like a long time drift. Sometimes they have kind of a some kind of curve, like a settling time over a few weeks. So that instrument that you're using, does it have a different principle that you don't have that problem, or is it the same kind of? Does it have the same problems? And I was back in the day, I was surprised how difficult it is to measure bottom pressure actually on scales several weeks. So is that the issue here, or is it not?
It's a good question. There's definitely, known drift within pressure sensors. For the time scale that we are interested in, it is not of concern. We don't, from our testing and validation of the RBR pressure sensors, they're extremely precise, extremely well calibrated, and over trying to measure storm surge over the course of, 1 to 3 days, the drift really should not be impacting that in any way.
Okay, thanks.
Great. Thanks for the question, Alex. Any other last final question? Okay, not seeing any. We're practically at the top of our hour, so I just want to thank everybody for joining us today as the second part of the NOPP Hurricane Coastal Impacts Forum. As a reminder, this is just one part of a multi-part series taking place over the next month. And in light of the upcoming holiday, our next session will take place in 2 weeks on Tuesday, July the 9th, at this very same time and using this exact same link. So I look forward to seeing all of you there, and I thank our speakers once again for their wonderful presentations, and also I thank Alex for allowing us the opportunity to piggyback on the webinar series that NOAA hosts regularly. So thank you all. Hopefully I will see you all in a couple of weeks.
Oh, thank you. Thank you, everybody.
Thank you, everyone.